In the beginning, there was silence. Not the silence of an empty room, nor the quiet of a sleeping earth, but the silence of nothingness itself, a stillness without space, without time, without memory. Then, without warning, that void was torn apart. A wound opened in the fabric of what would one day be called reality, and from it poured a fountain of light, heat, and motion to the human mind. It appears as an explosion, a cosmic bang reverberating through eternity. Yet, what if this eruption was not chaos, but emergence? Not a bang at all, but a release. Imagine a black hole reversed, a gateway not pulling matter inward, but throwing it outward in defiance. A white hole, the mirror of collapse, the paradox of creation. Could our universe itself be the single, impossible outburst of such an event? Could every galaxy, every star, every breath of life be the aftermath of a forbidden gate opening into existence? If so, then we are children of a paradox. The light in our skies is the echo of a cosmic impossibility. The laws of physics, which guard against white holes, may be written upon the very canvas that was born from one. This is the riddle. If the universe began as a white hole, then we are not living after a bang. We are living inside an eruption that never should have been. The story of the universe's beginning did not emerge in a single revelation. It was pieced together slowly through the eyes of astronomers staring into the night sky and the pens of physicists tracing equations onto paper in the early 20th century. The cosmos was believed to be static and eternal. The Milky Way was thought to be the entire universe, its stars suspended in an infinite, unchanging void. Yet mathematics whispered a different truth. Albert Einstein's general relativity, published in 1915, showed that space and time were not rigid backdrops, but pliable fabric. Gravity was geometry itself, bending under the weight of matter. In those equations lay the seeds of instability. The universe could not remain fixed. It must either expand or collapse. Einstein himself resisted this unsettling implication. To preserve cosmic stillness, he added a term to his equations, the cosmological constant, a balancing act to hold the universe in equilibrium. But nature had already set a different course. In the 1920s, Georges Lemaître, a Belgian priest and physicist, dared to follow relativity to its logical end. He proposed that the universe was once compressed into a primeval atom, a single point of unimaginable density that burst outward, setting space and time into motion. His vision was radical, unsettling, and ridiculed by many. Yet it carried with it the poetic power of beginnings, a universe born not in eternity, but in an instant. Soon after, Edwin Hubble stood at the eyepiece of the 100-inch telescope on Mount Wilson in California and saw galaxies racing away from one another. Their light stretched into the red, lengthened by cosmic expansion. The heavens were not static. They were swelling outward like a tide. The observation confirmed Lemaître's vision. The universe was not eternal in its current state. It had a birth. But if it had a birth, what was the nature of that moment? Here, the language of mathematics grew darker. Relativity suggested that winding back cosmic expansion would lead to a singularity, a point of infinite density, where the known laws of physics fractured into silence. It was in this landscape of thought that black holes emerged. In 1939, Robert Oppenheimer and Hartland Snyder described how a massive star could collapse under its own weight, shrinking past the point of no return. Later, in the mid-20th century, John Wheeler coined the term black hole, giving language to what had once been only theoretical. Roger Penrose and Stephen Hawking then expanded this frontier. Was another possibility, one almost heretical in its strangeness: the white hole. If black holes were singularities that nothing could escape, then white holes were their mirror twins, singularities from which nothing could enter, only escape. They were time-reversed black holes, spewing matter and energy outward instead of swallowing them whole. Too many physicists, the idea was dismissed as unphysical. White holes seemed unstable, forbidden by the second law of thermodynamics, and unsupported by observation. Yet the equations did not forbid them. They lingered like ghosts in the mathematics possibilities, waiting for interpretation. And then came the realization. The Big Bang itself looked eerily like a white hole, a singularity exploding outward, releasing all space, all matter, all time. The universe in its infancy resembled not a bang of destruction, but an eruption of creation. By the 1960s and 70s, whispers began to circulate among cosmologists. Could the primordial fireball, described by Lemaître and revealed in Hubble's galaxies, be the one and only white hole, the cosmic twin of collapse? In papers tucked away in journals, some researchers began sketching this connection. The Russian physicist Igor Novikov and others explored the possibility that white holes were not merely abstractions but cosmological events, linked to the universe's very birth. These were the seeds of an audacious idea, that our universe itself was born not from nothing, but from a gate predicted by Einstein's theory, a gate that in every other context appeared impossible. Thus, a paradox entered the heart of cosmology. Black holes had grown from mathematical curiosities into astrophysical giants, confirmed by observation. White holes remained their mysterious reflection, unseen, perhaps unreal. And yet, the greatest mystery of all, the origin of everything, bore their likeness. It was here, in the tension between observation and theory, between possibility and impossibility, that the question took root: did our universe begin as a white hole? In the cathedral of physics, there are ideas so strange, they are treated not as revelations, but as heresies. White holes belonged to that category. They emerged from the same equations that had given the world black holes, Einstein's general relativity, a theory that reshaped the human understanding of space and time. The mathematics was clear. If the universe allowed regions of space-time that collapsed inward, it must also allow their mirrors, regions that erupted outward. Yet, to physicists, this symmetry carried a sting. White holes seemed too wild to exist. They were ghosts of the equations, mathematical reflections, with no evidence in the sky. Unlike black holes, which had stellar deaths to justify them and galaxies to hide within, white holes appeared to have no physical cause. No mechanism could ignite them. No astrophysical process seemed capable of spawning such cosmic geysers. The problems ran deeper still. Entropy, the measure of disorder that always increases with time, rebelled against the notion. A black hole devoured matter, increasing entropy in keeping with the universe's thermodynamic script. But a white hole, by definition, would spew matter out in perfect order, as though time itself were running backward. Such behavior would defy the second law of thermodynamics, one of the most fundamental principles of nature, causality. 2. Strained under the idea, black holes had a future. Once matter crossed their horizon, its destiny was sealed. White holes, however, had no past. They could not be formed by collapse, nor birthed by any known process. They would simply appear, fully formed, already expelling matter. To imagine one was to imagine an effect with no cause, a violation of the very logic on which science rests. Stability offered the final blow. Even if a white hole were somehow born, physicists argued, the slightest touch of surrounding matter would destabilize it. A single stray particle drifting near its horizon would break the symmetry, triggering collapse and destroying the object in an instant. It was as though nature itself refused to tolerate their existence, and so white holes were banished to the margins. They became curiosities scribbled in notebooks, artifacts of equations rather than residents of reality. Scientists placed them in the same category as perpetual motion machines, fantasies permitted by symbols but rejected by the universe's laws. Yet, even as they were dismissed, the cosmos whispered contradictions. The Big Bang itself looked alarmingly like a white hole, a singularity bursting outward, releasing energy, matter, and space. From nothing, everything. A one-time event, never to be repeated, just as a white hole would be. The resemblance was too striking to ignore. Too many, this parallel felt like an affront. The Big Bang was already radical enough, a singularity where the known laws of physics collapsed into silence. To suggest that it was also a white hole, an object nature should forbid, was almost unbearable. It meant that the universe itself had chosen to be born in defiance of physics. This was the scientific shock. The cosmos seemed to behave like the very thing that equations allowed, but common sense denied. Black holes were supposed to be the ultimate monsters of physics, regions of no escape. But the universe revealed an even deeper enigma. Perhaps its own beginning was the reflection of those monsters, an eruption without precedent or explanation. Physicists found themselves staring into a paradox. If white holes could not exist, then why did the birth of everything resemble one? If entropy, causality, and stability denied them, then why did the cosmos bear their signature? For some, the contradiction was unbearable, and they left white holes behind as an unsolved puzzle, a curiosity not worth pursuing. For others, it became a source of fascination, a wound in physics, a riddle too powerful to dismiss. And for humanity, it raised a chilling question. If the universe itself is the impossible object, then perhaps the laws of physics are not as absolute as they appear. Perhaps reality itself was born in defiance of its own rules. If the universe had erupted like a white hole, the scars of that event should still linger in its oldest light. And so, physicists turned their eyes to the faintest whispers of the cosmos, the radiation left over from its fiery birth. This was the cosmic microwave background, the afterglow of creation, stretched and cooled as the universe expanded, yet still carrying the memory of its earliest moments. Technology finally caught up with the scale of this mystery. NASA's COBE satellite, launched in 1989, traced the sky with unmatched precision. It revealed that the microwave background was astonishingly uniform, the same temperature in all directions, down to 1 part in 100,000. It was as though the entire cosmos had been smoothed into near-perfection. But that uniformity carried a problem. Regions of the sky separated by vast cosmic distances, too far apart to have exchanged light or heat, were nonetheless identical in temperature. This paradox became known as the horizon problem. If nothing could have connected those regions, how had the universe balanced them so evenly? The answer, many believed, was inflation. In the early 1980s, Alan Guth proposed that in its first fraction of a second, the universe expanded exponentially, faster than the speed of light. In this picture, what now appears as distant regions of the cosmos were once close enough to share information, smoothing out their properties before being stretched apart. Inflation solved the horizon problem, explained the flatness of the universe, and matched the data beautifully. Yet, inflation itself was a radical hypothesis, untested and filled with unanswered questions. What field powered it? Why did it start? And why did it stop? For some, its elegance carried unease. It was a mechanism tacked on to the Big Bang, not a fundamental explanation of the beginning. And here, once again, the specter of white holes returned. Could the birth of the universe, if it resembled a white hole eruption, have naturally smoothed the cosmos without the machinery of inflation? If the universe were born in a single burst from a collapsing singularity, might its initial conditions carry the uniformity we now observe in the background sky? The Planck satellite, launched in 2009, deepened the mystery. It mapped the CMB with exquisite accuracy, revealing slight fluctuations, tiny ripples of temperature that seeded galaxies and clusters. These fluctuations matched the predictions of inflation with remarkable precision. Yet, some anomalies remained, a curious cold spot. Asymmetries in large-scale structure, features that inflation could not fully erase. To some, these imperfections hinted at physics beyond inflation, shadows of a deeper origin. It was in this context that quantum gravity, the dream of uniting relativity and quantum mechanics, entered the conversation. In loop quantum cosmology, space itself is woven from discrete threads, a granular fabric that prevents true singularities from forming. In these models, the collapse of a universe does not end in an eternal black hole. Instead, the compression reaches a quantum limit and rebound. The singularity is avoided, replaced by a bounce. A universe dies in collapse, and from its ashes, another is born in expansion. To those who studied such ideas, the Big Bang was not the absolute beginning. It was the rebound, of something older, something hidden behind the veil of time. From one perspective, such a bounce is indistinguishable from the eruption of a white hole. Both describe the same act. Matter and space thrust outward after a moment of infinite compression. Speculation grew bolder. Perhaps our universe was born from the collapse of a massive black hole in another cosmos. Inside that black hole, from the outside invisible, a new universe budded and expanded, its Big Bang appearing to us as a white hole singularity. This was not science fiction, but the logical extension of equations. Black holes and white holes as two sides of the same coin. The life and death of universes intertwined. The emotional weight of such an idea is immense. It suggests that every black hole in our universe may be more than a grave. It may be a womb, a bridge to another cosmos with its own stars, galaxies, and histories. And if so, our own beginning was not a bang from nothing, but the release of matter and space from a black hole beyond our perception. The CM, with its uniform glow and subtle imperfections, becomes in this picture not just a relic of a hot birth, but a fingerprint of an inheritance, a signature of collapse and rebirth written across the heavens. And so, deeper investigation did not quiet the white hole idea. It sharpened it. Every new telescope, every new map of the background sky, every model of quantum spacetime whispered the same unsettling possibility. The Big Bang might not have been a singular explosion into nothingness, but the outward pulse of a cosmic rebound. A white hole origin was no longer a fantasy confined to equations. It had become a contender in the most profound mystery of all, why the universe exists at all. At the heart of nearly every galaxy lies a darkness that defies imagination. Black holes, regions of spacetime so warped that not even light can escape their grasp. They are not merely objects. They are boundaries of knowledge, horizons beyond which human understanding collapses. From their edges, physics itself begins to unravel. The defining feature of a black hole is the event horizon, the invisible surface marking the point of no return. To an outside observer, matter falling toward it seems to slow, its light stretching endlessly into red until it fades into silence. But from the perspective of the doomed traveler, the fall is swift, unstoppable, and irreversible. Physics, as we know them, dissolve into paradox. For decades, black holes were seen only as devourers, eternal prisons of matter and light. But the deeper scientists studied them, the more their secrets resisted simplicity. In the 1970s, Stephen Hawking discovered that black holes were not entirely black. Quantum effects near the event horizon allow them to emit faint radiation, now called Hawking radiation. Over immense timescales, this radiation causes black holes to lose mass, shrink, and eventually evaporate. Even the greatest giants of the cosmos are not eternal. Yet this discovery only deepened the mystery. If black holes evaporate, what happens to the information contained within? The information paradox was born. Quantum theory insists information cannot be destroyed. Yet black holes seemed to erase it forever. For physics, this paradox was more than troubling. It was a wound in the fabric of science itself. And here, within the heart of the paradox, speculation began to grow bolder. What if black holes were not ends, but bridges? What if their singularities were not final deaths, but transitions, tunnels, into something beyond? In this vision, the inside of a black hole might not collapse into nothingness. Instead, it could rebound, expanding outward into a new region of spacetime. From the outside, we would see only a black hole, a void swallowing everything. But from the inside, it might appear as a white hole, an eruption of matter and energy, a big bang birthing a new universe. Such an idea turns the cosmos into a tree of worlds, each black hole a seed that blooms into another universe beyond our perception. The child universes may carry slightly different physical laws, their constants shifted by the conditions of collapse. In this way, black holes become both graveyards and wombs, endings and beginnings, connected by a symmetry that feels almost too perfect to dismiss. This line of thought was crystallized in the 1990s by theoretical physicist Lee Smolin, who proposed a theory known as cosmological natural selection. Just as living organisms reproduce with variation, universes might do the same. Each black hole births a new cosmos, its laws of physics subtly altered. Over countless generations, universes that favor the formation of black holes proliferate. The result is a multiverse shaped not by chance, but by evolution, fine-tuned through cosmic reproduction. The implications are staggering. If true, the universe we inhabit is not a singular, isolated reality, but one branch in a vast evolutionary chain. Every galaxy, with its central supermassive black hole, could be a portal to a new universe. Every stellar collapse could be the seed of another creation. The night sky, filled with black holes, invisible to the eye, becomes a nursery of worlds, each carrying the possibility of existence, each a potential mirror of our own. And then comes the disturbing symmetry. If every black hole can give birth to a universe, then our own Big Bang might itself be the child of another. What we call the beginning may be nothing more than an inside view of a white hole that rebound from a singularity in a parent cosmos. Our universe may have been born in darkness, hidden in the collapse of a star we will never see. This realization escalates the mystery to its highest stakes. It suggests that the Big Bang was not unique, that creation is not an isolated miracle. Instead, it is a pattern repeated across the multiverse, each universe begetting others in an endless cycle of birth and death. Yet, even in its beauty, the idea is unsettling. It removes the comfort of uniqueness. The cosmos is not a singular story, but an infinite library of narratives, each page written in the collapse of a star. We live not in the only world, but in one among uncountable generations. And the laws of physics we cherish may be local customs of our own branch, shaped by the inheritance of collapse. Still, in this vision there is poetry. The black holes that haunt our galaxies are not merely monsters. They are mirrors, reflecting the possibility that our own existence is the light of a white hole's eruption, that every horizon of darkness may conceal a dawn beyond it, the mystery deepens, not with answers, but with the weight of possibility. Black holes, once thought to be the end of all things, may instead be the most prolific creators in existence, and our own universe may be the echo of one such creation, a child born from the forbidden mirror of a black hole. The deeper the human mind peers into the abyss of beginnings, the more it finds itself surrounded by mirrors. The universe, born in an eruption of space and time, appears at once as a singular event and as part of a grander symmetry, an echo of processes written deep into the equations of reality. If the Big Bang resembles a white hole, then perhaps the universe itself is not alone. Perhaps it is one note in a symphony without end. To approach this mystery, science has reached for theories that live at the very edge of mathematics and imagination, models that try to stitch together the broken seams of general relativity and quantum mechanics. Among them, one idea has risen with quiet persistence: the Big Bounce. The Big Bounce, a universe that rebounds in loop quantum gravity. Space is not continuous. It is not a smooth fabric, but a granular weave built from tiny loops of energy that cannot be divided further. In this picture, the singularities predicted by general relativity, the infinities of density and curvature, are illusions born of treating space-time as continuous. At the smallest scales, space-time resists collapse, according to loop quantum cosmology. When a universe contracts under its own gravity, it does not fall into an infinite point. Instead, quantum pressure halts the collapse at a minimum volume. At that moment, the universe rebounds, expanding outward in a new cycle. The Big Bang becomes not a beginning, but a bounce, a transformation of contraction into expansion. To those who study these models, the bounce is indistinguishable from a white hole. It is matter and energy, once crushed, now released in a surge of expansion. A dead cosmos gives birth to a new one, each cycle connected through the forbidden doorway of a singularity avoided. Our universe, in this vision, may be the latest child in an eternal lineage of collapses and rebirths. Hawking, time, and the nature of singularities. The work of Stephen Hawking deepened this confrontation with singularities. In the 1960s and 70s, alongside Roger Penrose, he proved that singularities were not rare accidents of relativity, but inevitable outcomes of gravitational collapse and cosmic expansion. They were the boundary points of space-time itself, edges where time ceased to exist. Yet, Hawking also explored the role of quantum effects near these boundaries. His work on black holes and his reflections on the origin of time raised profound questions. If singularities are inevitable, are they truly beginnings and endings, or are they transitions to something beyond? Could the arrow of time itself emerge from such events? In one speculative line of thought, the eruption of a white hole is not only the release of matter, but the birth of temporality. The asymmetry of time, why the past is fixed and the future unknown, might be rooted in the irreversible burst of entropy carried in a white hole's expansion. In this sense, the flow of time we experience could be the direct inheritance of the universe's first eruption. The Ravelli-Haggard model black holes, reborn as white holes, more recently. Physicists Carlo Rovelli and Hal Haggard have advanced models in which black holes do not end in eternal singularities. Instead, quantum gravity effects cause them to rebound into white holes. To an external observer, the process might take billions or trillions of years, stretched by time dilation near the event horizon. But from the inside, the transformation from black hole to white hole could be almost instantaneous. In this picture, black holes are temporary. They collapse, stall, and then explode outward, reborn as white holes that release their contents back into the cosmos. On small scales, this could explain mysterious cosmic events such as fast radio bursts or unusual gamma-ray emissions. On the largest scales, it suggests that what we call the Big Bang may itself have been such a rebound, the white hole of a black hole from a previous universe. False. Vacuum decay and inflations. Alternatives. These models lies another possibility rooted in quantum field theory. The vacuum of space is not truly empty, but filled with energy fields, fluctuating at every moment. Our universe may inhabit a false vacuum, a temporary state of stability that could one day collapse into a more fundamental ground state, inflation. Theory itself arose from this quantum landscape. It proposed that a field of vacuum energy once dominated the universe, driving exponential expansion before decaying into matter and radiation. Yet some physicists have speculated that this decay is not unique to our cosmos. A false vacuum could spawn bubble universes, each emerging as a new expansion when the vacuum collapses locally. From the inside, such an eruption would look like a big bang, a burst of space and energy uncoupled from the parent vacuum. To the observer within, it would be indistinguishable from the eruption of a white hole. The laws of physics in each bubble may differ, set by the conditions of decay. Our universe may simply be one bubble among countless others, each with its own physics, each a white, hole-like eruption in the infinite sea of the multiverse. White holes as time reversed black. Holes math. White holes are nothing more than black holes run backward in time. They are mirror solutions to Einstein's equations, where collapse becomes expansion, absorption becomes eruption. In this symmetry lies a haunting suggestion. Perhaps time itself is not fundamental, but emergent. Perhaps what we call the forward arrow of time is only the experience of living within a white hole's unfolding. If this is true, then every moment of human life, every thought, every heartbeat, every star igniting in the night sky is part of the irreversible cascade of a white hole's expansion. Time flows only because the universe is still erupting, still unfolding from its impossible birth. The multiverse, an ocean of worlds from these threads. A vision emerges that is as staggering as it is unsettling. If white holes are real, then every black hole may contain a new universe. If false vacuums decay eternally, then bubble universes may be endlessly budding from the fabric of space. If bounces are real, then each collapsing cosmos may rebound into another. The implication is unavoidable. Our universe is not unique. It is one among an infinite sea, each born from a white hole eruption. each carrying its own laws, histories, and possibilities. Some may collapse quickly, others may expand forever. Some may allow galaxies, stars, and life. Others may remain sterile and dark, and yet, in this vast multiverse, one pattern repeats: birth from collapse, expansion from compression, eruption from silence. White holes become the universal motif, the heartbeat of creation echoing across realities. Philosophical reflections, children of an impossible fire for humanity. These speculations carry both wonder and unease. If the universe is a white hole, then our existence is the continuation of another cosmos's ending. We are not born from nothing, but from the ashes of a collapse beyond our sight. Every breath, every planet, every galaxy is the expression of that rebirth. The arrow of time, the laws of physics, the very possibility of thought, all may be consequences of that first eruption. And if universes reproduce endlessly, then existence itself is eternal, though no single universe is. We live in a lineage without beginning and without end, a family tree of worlds branching forever into the unknown. The mystery deepens, not with certainty, but with possibility. White holes, once dismissed as impossible, now haunt the edges of cosmology as symbols of creation. They are the mirrors of black holes, the eruptions that may seed infinity, the forbidden gates through which reality itself pours. Perhaps our universe is nothing more and nothing less than the light of one such eruption, a single flare in an eternal sea of fire. The greatest paradox of the white hole is not that it may exist, but that if it does, it hides in plain sight. For, by definition, a white hole is an object that cannot be approached, that ejects everything but admits nothing. It would live beyond horizons we cannot cross, its signatures subtle, fleeting, and easily mistaken for other cosmic phenomena. To search for it is to look for the unobservable, to reach into the silence between the stars and hope for echoes of an impossible. Birth. Whispers in the high-energy sky. The first hope lies in the most violent signals the universe sends. Gamma-ray bursts, some lasting mere milliseconds. Others, stretching for minutes, erupt from distant galaxies with a brilliance that can outshine all the stars in a universe for a brief moment. Most are thought to arise from collapsing stars or colliding neutron stars. Yet a fraction remain unexplained events with no clear origin, pulses of light that appear suddenly and vanish without trace. Could these be the death cries of microscopic white holes? Some theories propose that small white holes, relics from the earliest universe, might survive only briefly before exploding in a final release of energy. Such an event would be almost indistinguishable from a gamma-ray burst or a fast radio burst, those enigmatic millisecond-long flashes of radio energy that sweep across our telescopes from unknown sources. To some, these phenomena are the most promising places to search for white hole signatures, bursts of radiation that do not fit the catalogs of stars or galaxies, anomalies that hint at physics beyond collapse, telescopes that look back in time. The James Webb Space Telescope, with its deep gaze into the infinite, peers into the first hundreds of millions of years after the Big Bang. It cannot see the white hole itself. If such an eruption birthed the universe, but it can trace the conditions that followed, its images of the earliest galaxies, their unexpected maturity, and their strange clustering, press cosmologists to question whether inflation alone explains the young cosmos. If our universe began as a white hole rebound, some fingerprints may linger in the distribution of galaxies, in the way matter was seated, in the texture of spacetime itself. Meanwhile, ground-based observatories like LIGO and Virgo listen to the tremors of the universe, gravitational waves rippling through spacetime. These detectors have already captured the songs of colliding black holes, the final embrace of neutron stars. But in the years to come, next-generation instruments, the Einstein telescope in Europe, Cosmic Explorer in the United States, and space-based missions like LISA may have the sensitivity to detect stranger events, a black hole rebounding into a white hole, or a relic white hole decaying, could release a signature pattern of gravitational waves unlike any other. If detected, it would be nothing less than a direct clue that white holes are real, simulating the impossible where telescopes and detectors reach their limits. Supercomputers step in. Physicists now build simulations of universes within machines, testing what happens when general relativity meets the quantum rules of loop gravity. These digital experiments reveal bounces where singularities should be, expansions erupting where collapse was expected. They produce models of universes that resemble our own, but born not from nothingness, rather from transitions in these simulations. White holes emerge not as speculative fantasies, but as natural consequences of equations. By adjusting variables, researchers can ask whether the cosmic microwave background, the relic light mapped by COBE, WMAP, and Planck, carries the telltale fingerprints of a bounce. They can search for patterns inflation cannot explain, but a white hole origin might. The subatomic frontier at the smallest scales, particle accelerators, probe realms that may touch the same physics. At CERN, the Large Hadron Collider smashes protons at near-light speeds, creating showers of particles that briefly mimic the conditions of the early universe. Though it cannot recreate a white hole, it can test theories of quantum gravity that predict them. Extra dimensions, hidden symmetries, and new fields might all be revealed indirectly through collisions in the search for white holes. These experiments act as lanterns on the subatomic frontier, illuminating the pathways where relativity and quantum mechanics intersect. Each collision offers a fragment of data, each anomaly a potential clue that space-time itself may behave differently when pushed to extremes. Listening for echoes of the beginning, the frontier of observational cosmology now stretches to the largest scales. Surveys like Euclid, DESI, and the Vera Rubin Observatory will map billions of galaxies, tracing the shape of cosmic expansion across space and time. Within these maps, scientists seek subtle irregularities, deviations from what inflation predicts, signs that the universe's earliest conditions carried the symmetry of a white hole eruption. Even the polarization of the cosmic microwave background is scrutinized, for patterns that might betray a bounce, a twist in the polarization, a slight imbalance in temperature fluctuations. Could be the fossilized echo of a universe that did not begin in silence, but in rebound. The challenge and the hope yet, the search remains daunting. White holes may never reveal themselves directly. They may remain hidden behind horizons, their eruptions lost in the noise of other cosmic fires. But science has faced such challenges before. Black holes themselves were once dismissed as mathematical fictions, impossible objects. Today, their shadows are photographed by the Event Horizon Telescope. Their mergers heard across the cosmos in gravitational waves. What was once unthinkable is now observable. And so, hope lingers that white holes, too, may step from speculation into evidence, reflection, searching for our origin in the end. The quest for white holes is not only about physics. It is about origins. If our universe is the eruption of a white hole, then somewhere written in the fabric of space lies the evidence of our birth. To find it would be to glimpse the moment when time itself began to flow, to see the spark from which galaxies and minds alike were born. The challenge is immense, but the reward is ultimate, a chance to know not just how the universe behaves, but where it truly came from. And so, across telescopes, detectors, colliders, and simulations, humanity listens for the faintest whispers of an impossible fire, the echoes of a white hole that may have birthed everything. The universe begins and ends in silence. Not the silence of a paused breath, but a silence so profound that even time has not yet been born to count it. Out of that silence, something erupts: light, motion, matter, and the arrow of time itself. For centuries, humanity has named this moment the Big Bang. But if it was not a bang, not a beginning, but the release of a white hole, then what we call creation is, in truth, the death of something else. This possibility is unsettling and beautiful. It binds existence to a cycle of birth and death that mirrors the rhythm of nature. Stars ignite and burn, then collapse into darkness. Galaxies spin and fade. Civilizations rise and fall. And in the largest possible frame, even universes may collapse, only to rebound into new ones. The cosmos may be less like a line with a beginning and end, and more like a forest, a living ecology of creation, seeded by collapse, grown from endings into beginnings, the mirror of mortality for human beings. The question of origin is inseparable from the question of meaning. If the universe itself was born from a white hole, then our existence, our lives, our thoughts, our memories, is the continuation of a cosmic death. We are children of a parent universe we will never see. The atoms in our bodies are the ashes of another cosmos's collapse, reassembled in the fire of rebirth. This reflection echoes in our own mortality. Just as universes may emerge from black holes, so too do lives emerge from endings. Every birth is the continuation of countless generations past. Every death nourishes the future in ways unseen. The cycle is not foreign to us. It is written into biology, into culture, into the rhythms of existence. If the cosmos itself follows this law, then humanity is a microcosm of a truth far greater than itself. The longing for origins, the longing to know where we come from, is perhaps the most ancient of human questions. We have told myths of gods carving the heavens, of chaos tamed into order, of fire stolen to ignite the world. Today, science replaces those myths with equations and telescopes, but the longing remains the same. Behind every calculation, behind every satellite sent to map the cosmic microwave background, lies the same desire: to look into the abyss of silence before time and glimpse the fountain from which being pours. If the universe is a white hole, that fountain may not be a singular act of creation, but the ongoing cycle of cosmic renewal. We are not the first, nor will we be the last. Existence does not spring from nothing, but from the ashes of collapse, in an endless rhythm that binds the infinite to the finite. Universes as seeds, too. Imagine universes as white holes is to imagine them as seeds. Each one erupts, grows, and flourishes, only to collapse and give birth to others. Some seeds may scatter into sterile ground, universes without galaxies or life. Others may bloom into rich and luminous gardens filled with stars, worlds, and the possibility of consciousness. In this view, the multiverse is less a cold expanse of randomness and more a living cycle, an eternal orchard where each white hole is the seed of another cosmos. Death becomes not an end, but the fertile ground of rebirth. And if this is true, then the Big Bang was not the unique miracle of existence, but a natural flowering, one of countless blossoms in the infinite field of being. The weight of meaning. But what does this mean for humanity? Fragile and brief, inhabiting one small planet in one quiet corner of one universe. It means that our lives are part of a chain that cannot be broken. We are not accidents of chance, not fleeting sparks in a void. We are inheritors of a lineage that stretches beyond stars, beyond galaxies, beyond even the universe itself. Every moment of thought, every act of love, every question whispered into the night sky is bound to that eternal cycle. To live is to be part of a story written not in words, but in the birth and death of universes. This realization carries both humility and wonder. Humility, because our universe is not the first and will not be the last. Wonder, because we are here, conscious, breathing, able to ask the question at all. Out of collapse and fire, out of endings and rebirths, came the possibility of eyes that can look back into the abyss and wonder why. Time's arrow and the fire of Behemoth. The white hole is the source of our universe. Then the arrow of time itself, the flow of past into future. The impossibility of reversal may be its direct inheritance. The eruption of a white hole is irreversible, a surge of entropy that sets the direction of time. All of human experience, from memory to mortality, is an echo of that first cascade. To exist is to ride the wave of time, pouring outward from the impossible fire of birth. We are not merely in the universe. We are carried by its unfolding, borne along by the asymmetry born in that first eruption. Time flows because the white hole opened, and in that flow, all stories, cosmic and human alike, are written. The eternal Chenef universes are born from white holes. Then we are part of an eternal chain. Each cosmos dies into collapse. Each collapse erupts into rebirth. The chain has no beginning, no final end, only transformation. In this vision, immortality is not the persistence of a single universe or a single life, but the continuity of the cycle itself. Human mortality is softened by this reflection. Death, in this frame, is not a void but a passage, a contribution to the cycle of becoming. Just as stars die to form new stars, just as galaxies merge to seed new galaxies, so too may universes collapse to birth new worlds. We live inside one link of that chain, one expression of a rhythm older than time itself. The final reflection is, the narrative closes. One image remains, a white hole erupting in silence, releasing light, matter, and time into the void. That eruption may be the reason galaxies shine, the reason atoms form, the reason human beings can wonder. If so, then everything, the laughter of children, the death of stars, the spiral of galaxies, is testimony to the impossible fire of that first eruption. And so, in the stillness of reflection, the conclusion comes. Perhaps we are the light pouring from a darkness we will never see, the living testimony of a white hole's impossible fire.